Now I'm going to show you a circuit that's called a voltage divider. This is a name we give to a simple circuit of two series resistors. So I'm just going to draw two series resistors here. And it's a nickname in the sense of it's just a pattern that we see when we look at circuits. And I'll show you what the pattern is. The pattern is we have two resistors in series. It's no more than that. And we assume that there's a voltage over here. We hook up a voltage over here like this. So that's called an input voltage. We'll call it VI for V in. And then the midpoint of the two resistors and typically the bottom, that's called V out. So we basically just have a pattern here with a series resistor driven by some voltage from the ends of the two resistors, and we're curious about the voltage across one of them. So now we're going to develop an expression for this. Let's also label our resistors. This will be R1 and this will be R2. That's how we tell our resistors apart. And we're going to develop an expression for this. So let's first put a current through here. We'll call that current I. We'll make an assumption that this current here is zero. There's no current going out of our little circuit here. And that means, of course, that this current here is also I. So it's continuous all the way down. And now we want to develop an expression that tells us what V out is in terms of these two resistors and the input voltage. So let's go over here and do that. First thing we're going to write is we know that using Ohm's law, we can write an expression for these series resistors on this side here. Ohm's law we'll put over here, V equals IR. In the specific case here, V in equals I times what? Times the series combination of R1 and R2, and the series combination is the sum, R1 plus R2. I'm going to solve this for I. I equals V in divided by R1 plus R2. All right, next step is going to be, let's write an expression that's related to V out. And V out only depends on R2 and this current here. So we can write V out equals I times R2. And I'll solve this equation for I the same way, equals V0 over R2. And now we have two expressions for I in our circuit. Because we made this assumption of zero current going out, those two I's are the same. So let's set those equal to each other and see what we get. I is V0 over R2 equals V1 over R1 plus R2. So now I'm going to take R2 and move it over to the other side of the equation, and we get V out equals V in times R2 over R1 plus R2. And this is called the voltage divider expression right here. It gives us an expression for V out in terms of V in and the ratio of resistors. Resistors are always positive numbers, and so this fraction is always a less than 1, which means that V out is always somewhat less than V in, and it's adjustable by adjusting the resistor values. It's a really handy circuit to have. Let's do some examples. We'll put that up in the corner so we can see it. Real quick, I'm going to build a voltage divider that we can practice on. Let's make this 2K ohms, 2,000 ohms. We'll make this 6,000 ohms or 6K ohms. And we'll hook it up to an input source that looks like, let's say it's 6 volts, like that. And we'll take an output off of this. Right here is where the output of our voltage divider is. And we'll say that that is V out, V out. So let's solve this using the voltage divider expression. V out equals V in, which is 6 volts, times the ratio of resistors. And the R2 is 6 k ohms divided by 2 k ohms plus 6 k ohms. And notice this always happens. The k's all cancel out. That's nice. And that equals 6 times 6 over 2 plus 6 is 8. And if I do my calculations right, V out is 4.5 volts. So that's what a voltage divider is. And if you remember at the beginning, we made an assumption that this current going out here was about 0. If that current is really small, you can use this voltage divider expression, which, as we see up here, is the ratio of the bottom resistor to both resistors. That's how I remember it. It's the bottom resistor over the 2 resistors added together. If you think the current is not very small, what you do is you go back and you do this analysis, you do this same analysis again, but you account for the current that's in here. So that's the story on voltage dividers.